Hi, this is Professor Fernandez, and this is the video for Lesson 16, Module 2. We're talking about flux and circulation in this module. So I'm going to go through this definition to begin with. I'm going to remind you of some of the things that we did in the first video in this lesson. So the first part of this definition says, let C be a simple, piecewise smooth, counterclockwise oriented curve in the plane. So we've seen these terms before: piecewise smooth, counterclockwise curve in the oriented curve in the plane. The simple part here is slightly new. I discussed this very briefly in the first module's video, but simple basically means that the curve does not have any self-intersections. So that is not a simple curve. This is a simple curve. So other than that, we are looking in this definition for C to be piecewise smooth. So it could look like this, it could be smooth in pieces. That's fine as long as it doesn't self-intersect. And then we want it to be clockwise oriented. So all of these curves, we would be going in this direction as we sweep out the curve. So that's basically what the curve C looks like. And then let's see what else is in here in this definition. So we have, suppose R of t is a parametrization of C. So I know x of t, y of t, for example. I'd parametrize each of the points along C. And t is between a and b. Suppose also that the vector field f has two components, f and g, which are differentiable. I can find their partial derivatives on some region containing C. So in other words, whatever curve C is, I want to make sure that the vector field is defined on an open set that contains the curve C. We won't get into the sort of technical details about that because most of the time the calculations we'll be doing will involve vector fields that are defined everywhere in the plane. So here are two additional definitions. So when C is closed, so what is a closed curve? A closed curve is a curve that looks basically like that, or you can kind of smooth it out. It's a curve whose initial point is the same as the terminal point. So that's a closed curve. When C is closed, we define the circulation of the vector field around C to be this. Now, hopefully this looks familiar because this is exactly what we talked about in the previous module, Module 1. On the left-hand side, you remember that we had gotten to this by thinking about the notion of work in physics, and we had first thought of this quantity as f dot dr. So in that context, we came to this quantity by thinking about the force F, or the vector field F, pushing a bead along the curve C, and thinking of C as a wire, and then thinking about the sort of energy that the force F, it took the force F to do that as it actually moved the bead. And that gave rise to what we called here these vector line integrals. Here we're introducing this in a completely different context. We're thinking of this now as the circulation of the vector field. And again, we teased out these notions in the previous Module 1 video. So the new concept here really is, not just a rephrasing of what we already know, like this one is this flux. So down here it says when C is closed or not, in other words, C does not have to be closed for this definition, we define the flux of F across C as this new line integral. So I'm going to tell you what this is in a minute. Long story short, this n here is the normal vector to the curve, which is kind of the complement, if you will, of t, the tangent vector to the curve. And then in a moment you'll see, I've pre-drawn some things down here. We are going to derive how this left-hand side vector line integral turns into this thing you see on the right-hand side. Okay, so that's this definition. What I want to do now is motivate this new concept here, the flux, and why it's this and how it's equal to that. And then come back later on and give you some intuition about what the circulation measures, what the flux measures. Some of it will be familiar, some of it will be new. So on to this concept and how we get there. So I'm going to zoom in here to just remind you of how we got to the first concept, which was circulation. So we were thinking about this bead, as I mentioned, on this curve C, and a vector field, maybe like a wind field, moving or trying to move the bead around this the curve C. So that's the picture that's over here. And we had seen that the tangential component of the force F that the bead is actually feeling when it moves or along the curve C is given by the dot product of F with the tangent vector T. So I've put that in green here in the picture. And I mentioned at the moment in that video, in the Module 1 video, that we were ignoring motion in the perpendicular direction, in this direction, and that we come back to it. So this is where we are coming back to it. So now I am going to look at the normal direction. So I'm not any more interested necessarily in a bead moving along a wire, the curve C. I'm interested more in thinking of now a different context where C is kind of a fictitious curve. And I'm thinking of flow of a fluid across the curve C. So I'm thinking now of not necessarily moving beads, but maybe think of C as a fictitious curve in space that you could draw with your finger. And then maybe you are immersed in a rain shower, and rain is falling. And as the water droplets fall, they are moving through this fictitious curve C. So that's kind of the rough intuition I want you to have. And the notion is how much fluid is moving through the curve C. So that's where we're getting to this notion of flux. To measure that, we're really interested there in the normal component. In other words, we're thinking about fluid flow through the curve C, not along the curve C, as we were thinking about with circulation earlier. So the normal component of this field F that I've drawn here is F dot n, where now I'm taking the dot product with this vector, which is the normal vector. So that kind of explains already a little bit about why this integrand is what it is, but I do want to unwrap it to tell you how it turns into this thing on the right-hand side. To do that, we have to talk a little bit about the normal vector to the curve C. So I've drawn it here, but I want to give you a different perspective. So here is a perspective that's going to help us actually determine what the components of the normal vector are. I want to make one little comment on this before we head off to do that. I've put in here the orientation that is assumed in the theorem. So notice that this curve here is traced out in that direction in the plane. So that's the counterclockwise direction that is assumed up here in the theorem. So I had not put that into these two pictures because those two pictures were just intended to give you an intuition about, now with flux, we are going to care about the movement of the vector field across the curve, not just tangent to the curve. Okay, so the picture I've drawn here is intended to relate the normal vector to the tangent vector to this vector k hat, the third standard unit vector. And you can see from the way that I've drawn everything here that the normal vector is the tangent vector cross k hat. And again, we're applying the right-hand rule here to tell us that. So if I start writing that out, my tangent vector, well, this is tangent to the plane curve C, so it has two components. Its components are tx and ty. If I view it as a vector in 3 space, then I would have a 0z component. So that explains why this vector looks like that. And then the vector k hat, this is a standard unit vector pointing in the z direction, has component 0, 0, 1. So I've done this cross product out for you, and this is the vector we get. And then now we have to remember that the tangent vector is a unit vector, and remember its definition is the derivative of r divided by its norm. So its components are x prime of t divided by the norm, and then y prime of t divided by the norm, where x and y are the parameterization components, the components of the parameterization of r. Okay, so remembering that. So in other words, this tells us that this is tx, x prime over the norm, and this is ty, y prime over the norm. So now we've calculated that the components of our normal vector, the first one is ty. So then I basically take this quantity and I put it in as the x component of the normal vector. And similarly, the second component of the normal vector is negative tx. So I take this quantity, I put it in there, and then I make it negative. So this gives us the components of the normal vector. And again, the normal vector is normal to the curve. so it lives in the xy plane, so it's z component 0. Great, so now we have the normal vector, and what can we do? So I'm going to go over here, and then I'm going to start writing this out, right? So like we talked about earlier, this is the component of the force that is normal to the fictitious curve C we're thinking about. And then what we're doing here with the line integral is we're adding up all of those contributions as we go along the curve C. So we really are looking for the net movement orthogonal to the curve C, the net flux through C. And that's what this quantity is. And then now we're going to say, great, so the vector field F is a plane vector field in this theorem. I will scroll back. It only has two components. So as I did here in this picture, when I started viewing the tangent vector as a vector in a 3 space, and also the normal vector as a vector in 3 space. Doing a similar thing here, so we're viewing the vector field F as a vector field in 3 space with z component 0. And here is the normal vector expression that we just discussed, the one from over here. And then, so that's f dot n, and then ds, we know that from lesson 13 is norm of r prime times dt. So now we see that there's some nice cancellation that's going to happen. After I calculate this dot product here, I'm going to get f times this plus g times that. But this norm of r prime in the denominator is going to cancel with that norm of r prime. So all that's left is f times y prime dt, that's what's over here, and then plus g times negative x prime dt, so that's what's over here. Great, and then last little bit to remember is that x prime, y prime of t dt, this is dy, and x prime of t dt, this is dx. So my final simplification of this right-hand side yields, that should be a y, yields the expression that we see in the definition. So that gets us back to, trying to put it on the same page here, that gets us back over here. Okay, so to recap, if I am looking at a sufficiently nice curve, it is simple, it doesn't self-intersect, it's piecewise smooth, oriented counterclockwise, and we're still in the plane. And then I parametrize it. And then all of a sudden, I immerse this curve in a vector field, planar vector field. So there's a bunch of vectors that are pointing in all sorts of different directions at every point. And I assume it's a nice enough vector field. I can differentiate it, for example. Then I can define two quantities, one of which is familiar. This is the circulation around C. So this gives me the notion of, we're thinking of the curve C now as a wire, and there's a bead on this wire, and the vector field pushes the bead around. And the circulation measures that. I can define a new notion of now, rather than thinking about C as an actual wire, think of it as a fictitious curve. It definitely helps to think of it as closed, although it doesn't have to be. And then we're thinking about, the vector field as being a fluid field, so maybe drops of water that are rushing in all sorts of directions. And then the flux then is going to measure effectively how much of the water is flowing through the curve, across the curve. And that's this new quantity on the left-hand side. And then we have this expression we derived that'll help us to calculate it. Okay, so much of what is written here is what I just said, but I do want to go over it because it contains some of those insights in a condensed form. So again, suppose that F is the velocity field of a fluid. So think of, standing in a stream, for example. The circulation of F around C basically measures how much F moves a small particle on C around C. So again, we're back to the bead on a wire interpretation. Here's another useful tidbit. A positive circulation implies that the motion occurs in the counterclockwise direction. That is the direction that we assumed in this theorem the curve was oriented in. So if F is moving in the direction of the curve, the dot product of F with the unit vector t will be positive, and then as we add this, we'll get a positive number. On the other hand, a negative circulation, if you calculate the circulation, you get a negative number. It implies that you're moving in the clockwise direction. In other words, opposite the direction of the curve that the curve is being traced out in. Okay, the second one for flux, so the flux through C is a measure of the net amount of fluid that moves through C. So again, picture yourself standing in the stream, and maybe you bring a hula hoop with you and you put it on the stream and you hold it so it doesn't fly away or float away. Then you can see a lot of fluid passing through this hula hoop. And think of that as your curve C. At some points, fluid will be passing faster than others. So, if you only think about the fluid passing orthogonal to C, then you really are calculating the flux. And as you add up all those contributions of outflux with influx, you get the net flux, which is the flux that we define in this definition. So a positive flux implies that more fluid passes through C in the normal direction than its opposite direction. A negative flux implies more fluid passes through C. In other words, more fluid goes into the curve C. I'm thinking again here of C as closed, but it need not be. When C is closed, definitely, then we say that F acts as a source if the flux through C is positive. We'll soon relate this to the vector fields we've been seeing in the previous module. Or a sink if the flux through C is negative. This should kind of make sense. Source is like things are emanating from somewhere inside your closed curve C. So there's stuff that's going to be penetrating the boundary. There's going to be a positive flux. A sink is, things are being sucked into the region that your curve is enclosing. So there's going to be a negative flux. There's going to be flow orthogonal to C. Okay, so as was the case with our definition that defined the work and vector line integral associated with it, notions of circulation and flux can give meaning to the line integrals we were studying in lesson 13. So, in this lesson, we're just adding more and more different ways to interpret and, in some sense, visualize the line integrals that we were working with in lesson 13 that we did not necessarily have a way to visualize back then. So let me do an example for you. Let me go back to example 16.1. Let's use the same curve C, which is the unit circle centered at the origin and traced out once counterclockwise. So we are going to once again evaluate a vector line integral, but this time we're going to evaluate the flux across C. And we're going to do it for the same two vector fields that we did in that example. So I say then compare your results to example 16.1 and interpret them in terms of circulation and flux. So let me remind you what we already did in example 16.1. So for this vector field here, we had calculated that what at the time we called effectively work, or the vector line integral, was equal to 2 pi. So we now have a new interpretation for this, and this is the circulation. So the fact that the circulation now is positive for this vector field tells us that if I draw this curve C, which is the unit circle centered at the origin, this vector field F, which is this one over here, is pushing this bead around this unit circle wire in the same direction, in this case counterclockwise, that the curve is traced out. So if I scroll down and remind you, here is the plot of that vector field. Again, we draw our unit circle here, traced out counterclockwise as I just did. You can see, of course, that if I put a little bead here, this bead is going to be pushed around because all of these vectors are pointing in the counterclockwise direction. It's going to be pushed around in this counterclockwise direction. And if I wait until it's pushed around exactly once, so it sweeps out the curve once, then the circulation is 2 pi units. And again, we won't talk about the units here because we have no information about units for the vector field F or any of the X or Y measurements. Okay, but in other words, we have positive circulation. The vector field moves the bead in the same direction that the curve is traced out. Okay, so how about over here? So we had talked in that example about the fact that when we did this second vector field over here, this one, 2x, 2y, which is a conservative vector field. In fact, both of these, I believe, are conservative. But anyway, don't quote me on that. We would have to check that. This vector field is definitely conservative, and we had calculated its line integral to be 0. So if we go back and look at its vector field, if I draw the same unit circle, Let me use the same color as before. We notice that the vector field, because it's orthogonal everywhere to this unit circle, makes sense because the unit circle is one of the level curves of the potential function of this vector field. And we know gradients, which is the vector field, are orthogonal to these level curves. So anyway, because the vector field is orthogonal to these to this curve, then the vector line integral from module 1, that work integral, which we now know as circulation, it makes sense now that it's 0. Because if I put my bead here, there is no movement that the vector field generates that goes along the curve. The bead would just stay there. It feels like it wants to be pushed out away from the origin. You know, if I freed it from this blue unit circle curve, so already we have a sense that if we calculate the flux of this vector field through this same curve, we're going to get a positive number. Because, again, if we removed the actual wire, the curve C here, but we kept the bead, the fact that the vector field pushes everything out, we would see some movement, and we'd see movement of this bead away from the origin. So we already have a sense that for this vector field, this red one up here, we're going to get a positive flux, but we'll calculate that in a minute. Same thing over here. If I start talking now about flux, this vector field on the left here is effectively everywhere tangent to the curve C that we were looking at. So, you know, it has no normal component. So this bead is just being, you know, moved and rotated around the circle, but it's not feeling at any point along the circle any push in the normal direction because the vector field vectors are already tangent to this circle. So we expect, in this case, to get a 0 flux. We expect that if we were to remove this fictitious wire of a circle and just let the bead roam free, it would still rotate, but it would not fly out or fly in. No net flux, so we would assume, or we would expect, that the flux would be 0. So, given all that, let's go off and actually calculate the flux for these two vector fields. So I'm going to start by writing down our expression for the flux. That's f dot n ds. And then writing out what this translates into based off the work we just did. So for the vector field over here, I have minus y and x. And then over here, remember this, if I scroll back up from the work that we did, is this quantity. So I'm actually going to write this out instead. It's a little cleaner. So we're going to say f dy minus g dx. Okay, and I know that the f in this case is negative y. Oops, I don't know what happened there, but I will try to get back to where we were, more or less. Oops. Okay, so it seems to have erased a lot of what I did, but that's okay. Okay, so we'll start all over again. So we were calculating negative y dx, negative y dy, so that is f dy, and then minus g dx. So the g here is just the vector field x, so that's x dx. Okay, and we had parametrized this as a circle, and remember that in that parameterization, x was equal to cosine of t, so maybe I'll write it down here somewhere. X was cosine of t, unit circle. Y was sine of t. And we had our derivatives, negative sine t and cosine of t. So now we're just going to substitute everything into here. So we get negative y, that's negative sine t, times dy, that is cosine of t. And there's going to be a dt here that's going to be common to both terms. And then we do minus x, which is cosine of t, and then dx, which is negative sine of t. Great. And my integral here is going through from 0 to 2 pi. We're sweeping out the circle once. So now let's see what I have in the middle here. So I have minus cosine times sine plus cosine times sine, so those cancel out. So I get 0 for my integral. And this is, again, what we expected to get. This is the flux of this vector field, which is a rotational vector field, that one. This is the flux of this vector field across this curve C. And again, we can see that because it makes sense because the vector field vectors are tangent to the curve C. So there's no movement orthogonal at any point along the curve generated by this vector field. Okay, so we have a 0 flux there. So now let's go off and calculate the flux as the second example for this other vector field. So similar thing, I'm calculating f dy minus g dx. And in this case, the vector field is different. So f is 2x dy minus, and then g is 2y dx. And then I go back and I use my same 0 to 2 pi in dt, but now I'm jumbling the integrand in a different way. So I'm going to pull out the 2 here because it's common to each one of these, and then I have x times dy, so x was cosine t, and then dy, looking down here, was cosine t also, cosine t, minus y was equal to sine t, and then dx we get from over here, which is negative sine t. All right, so this time around I have cosine squared plus sine squared, so that's equal to 1. And this integrates to 2 pi, so I get 4 pi. So as expected for this other vector field, I have a non-zero flux. Moreover, I have a positive flux. So this tells me, if we go back to our interpretations here, that the vector field f is acting as a source because the flux through C is positive. So a positive flux means that there's more fluid passing through C in the normal direction than in its opposite direction. So if I go through here and illustrate that, I'm going to draw, oops, let me use this marker, this pencil. I'm going to draw the unit circle, that's the curve C. And, I'm going to draw the normal vector at these points. And you can see why things have ended up being how they've ended up being, because the vector field points exactly in the direction of the normal vector at every point on this curve. All of the red arrows point in the direction of all the green arrows. So if you think about this curve C as being this kind of fictitious circle or this kind of hula hoop analogy, and you think of the vector field as being the velocity field of water in a stream, then it is rushing by this curve C at in exactly the same direction at all points. It's going out of the curve C. So there is fluid moving through the curve C, and it's all moving in the same direction, moving outward. So all of those f dot n contributions that are the integrands of our flux, these are all positive. The vector field f and the normal vector are all in the same direction. And then we're adding them up along S, so we get a positive number, specifically 4 pi for this example. Okay, so that's just a very quick calculation, couple of examples for you of flux. So now hopefully you have a much better understanding of what these line integrals represent. We, in the previous module, had given them, at least the first one, the interpretation of the work done by the vector field F in pushing a bead around a fictitious wire C, which was mathematically our curve. Now we can also understand it as the circulation of the vector field around that curve. This one does require that the curve C is closed. The vector line integral stuff that we were doing in Module 1 did not require that this curve C was closed. So, I want you to have those two potential interpretations at the ready in case you need them. The new one here is certainly the flux. So whether C is closed or not, although it helps to think of C as closed, we define this new line integral as the flux across C. And then certainly the last thing I'll mention is make sure that you get a chance to internalize and think about what the circulation and flux means. We will talk more about it in the next module, but hopefully reading through this and then going back and revisiting the examples we did gives you a good enough sense of why the flux and circulation values that we got are what they are for these two example vector fields. Okay, so I'll see you in